Welcome to this topic of the Demystifying IPv6 course on IPv4, IPv6 transition. This topic is actually part 2 of the IPv4, IPv6 transition, so we'll be picking up where part 1 left off. Just a reminder, in part 1 we talked about dual stack or IP layer, DNS infrastructure, and we started our discussion of IPv6 over IPv4 tunneling. In part 2 we'll cover more specific examples of IPv6, IPv4 tunneling, as well as some translation mechanisms. So just a reminder from part 1, there are basically two different types of tunnels: configured tunnels, which require the endpoints to be configured manually, and automatic tunnels, where the IPv4 address is embedded in the IPv6 address, and the tunnel endpoints are determined automatically. In this part 2, we'll talk specifically about ISATAP, 6-4, 6RD, and Teredo. ISATAP stands for Intra-site Automatic Tunneling Addressing Protocol and is described by RFC 5214. It is a host-to-host, host-to-router, or router-to-host automatic tunneling technology, so it's always got at least one host at either end. It provides basic unicast IPv6 connectivity between IPv6 hosts across an IPv4 intranet, hence the term intra-site. ISATAP hosts do not require any manual configuration. It's automatic by the protocol stack to create ISATAP addresses using standard address configuration mechanisms. Hosts create a linked local IPv6 address from a configured IPv4 address. So as the graphic below depicts, the IPv4 address is actually embedded as the least significant 32 bits of the host IPv6 address. So an IPv4 address is configured on the host, and it can automatically derive an IPv6 address from that. It uses the next significant 32 bits with the value 0000:5EFE and the most significant 64 bits as the global or local unicast prefix. So as described in this slide, it can configure itself with at least a linked local IPv6 address, or if there's some automatic mechanism, either router advertisements that it can receive or a DHCP-v6 server, it can configure its global unicast prefix that way. So ISATAP components are depicted in this slide. It could be just two ISATAP hosts connected to an IPv4 infrastructure. So it could be your own intranet in your own company. And when you turn on the IPv6 stack in the host, if it's a Windows machine, it can automatically derive a linked local address based on its configured IPv4 address, even though that IPv4 address might be derived via DHCP-v4. And then the two ISATAP hosts could actually communicate directly with each other without any further interaction from the IT department in the company, and exchange IPv6 datagrams over the IPv4 infrastructure. As I mentioned before, if there is an ISATAP router connected to the same IPv4 infrastructure, it can announce using router advertisements an IPv6 prefix to ISATAP hosts over the IPv4 infrastructure, and they can configure a global unique routable IPv6 address that way. And then those IPv6 packets that are destined off-net, in other words, even possibly for the IPv6 global internet, can be routed through the ISATAP router. So the previous slides described an intranet solution for automatic IPv6 over IPv4 tunneling. What about a mechanism for doing that over the global IPv4 internet? So RFC 3056, also referred to as 6-4, has described a mechanism for that. Keep in mind that there is a more current method for doing this type of connectivity called 6RD, which we'll cover later on. But let's start out and look at the way it was originally envisioned to do so, and in fact actually did do so for some time. So as it's As this slide mentions, it is a router-to-router automatic tunneling technology. It provides unicast IPv6 connectivity between IPv6 sites and hosts across the global IPv4 internet. It uses a specific prefix of 2002 : followed by the next 32 bits, which would be an IPv4 address, : /48, giving you 16 more bits to configure IPv6 subnets, and then of course the last 64 bits was going to be a host identifier. So actually requiring a 2002 prefix is a major drawback of 6-4, hence 6RD. Embedding an IPv4 is its second major drawback. Remember, we're running out of these, so this won't work on a globally wide basis, at least not for the foreseeable future. But it does give a full /48 to a site based on its external IPv4 address. So one external IPv4 address can be used by an entire intranet of IPv6. IPv4 external addresses are embedded in the 2002 prefix as I described above. So the next 32 bits following the 2002, giving you a /48. So another way to express that is a 2002 : the IPv4 address, : the 16-bit subnet, : /64. So the full 64 address looks something like 2002 : wwxx : yyzz : subnet ID : interface ID. And finally, there must be at least one router acting as a relay between the 6-4 domain and a given native IPv6 domain. So this slide shows you the 64 components in a wider spread basis. I'm going to go ahead and zoom in on various of these components as we discuss this. So to start with, at the bottom, Site 1 is a native IPv6 subnet, although it is a native 6-4 subnet, so the IPv6 prefixes start with 2002 : the IPv4 address of the 6-4 router 1 connected to router 1, which is 11.0.0.1. Now, consider in this example that the IPv4 internet can route 11.0.0.1 and also knows how to reach 12.0.0.1, 13.0.0.1, but again, since it's a global IPv4 internet, it should be able to route any public IPv4 address. So consider a 6-4 host in Site 1 wants to communicate with another 6-4 host on Site 2. And so it will formulate a source and destination IPv6 address using the 6-4 prefix, 2002 followed by 11.0.0.1 for its source, and then an IPv6 6-4 address with 12.0.0.1 as a destination, which are the corresponding IPv4 addresses of 6-4 router 1 and 2. Once those are encapsulated in an IPv4 address with 11.0.0.1 as a source and 12.0.0.1 as a destination, then that can be routed through the global IPv4 internet. And in turn, router 12.0.0.1 can strip off the IPv4 and forward the raw IPv6 6-4 packets from host on Site 1 to the host on Site 2. Of course, the reverse would hold true back for the reply. Now in this example, 13.0.0.1 is actually a 6-4 relay router, and a 6-4 relay router is one that has a link into the IPv4 global internet and a link into the IPv6 global internet. So it can relay 6-4 packets to the IPv6 internet and vice versa. So again, if the host in Site 1 wants to send a packet to a host on the global IPv6 internet, it would still use its 6-4 address as a source, but then it would just use a global IPv6 address as a destination, and the 6-4 router 1 would have to know to deliver that to the 6-4 relay router 13.0.0.1. And so it would use a source IPv4 address of 11.0.0.1 and send it to the destination 13.0.0.1. The relay router would receive it, de-encapsulate the packet, and send it to the IPv6 internet. Now, as you can imagine, there may be some routing issues when we're going from 6-4 to the IPv6 internet and back. So the IPv6 internet needs to know specifically which relay router and therefore which IPv4 link to use to get to the appropriate 6-4 network and vice versa. So there are going to have to be some manual interaction with the routing protocols, BGP4+ specifically, in order to make that happen. So here we have an example of using the two techniques, both ISATAP for intra-site and 6-to-4 to route between sites over the global IPv4 internet and even to the IPv6 internet through a relay router as described before. So locally, the ISATAP hosts would configure themselves based on their IPv4 addresses with an ISATAP address where the interface ID has the value 5EFE followed by the 32 bits of the IPv4 address that the host gets. And then the ISATAP router, which in this case is also a 6-to-4 router, will announce a prefix, a 6-to-4 prefix though, that the ISATAP host will use, and then it will combine its 6-to-4 address, the 2002 prefix, with its ISATAP address with the embedded IPv4 address as the least significant 32 bits. And of course it's going to use the IPv4 sides of the IP as also part of the 6-to-4 address. So in the case of 6-to-4 router A, the 157.54.0.1 translates to 9D36:1 and with the prefix of 2002. So when ISATAP host A wants to communicate with ISATAP host B, it can use the 6-to-4 addresses and use that across the IPv4 infrastructure that they're directly connected to using the ISATAP mechanism of tunneling. But when they want to communicate to the IPv6 internet, they could also encapsulate those directly over their IPv4 infrastructure, but then it will be routed through the IPv4 internet via the 6-to-4 routers and to the 6-to-4 relay routers as previously described. So 6-to-4 worked fine for a while, but the limits were already noted previously. But instead, 6RD was defined by RFC 5569 as a better way. So 6RD refers to IPv6 rapid deployment on IPv4 infrastructures. It facilitates IPv6 rapid deployment across IPv4 infrastructures of internet service providers. 6RD facilitates IPv6 rapid deployment across IPv4 infrastructures of ISPs, not necessarily the global IPv4 internet. It was, however, derived from 6-to-4, but only operates within a single ISP. RFC 5569 is only 9 pages, so obviously it's a very simple implementation, although it does derive some of its functionality from 6-to-4, so it references to that as well. So a little bit of the history of 6RD. It was first proposed in November 2007, and a service provider in France immediately decided to implement the solution. It was so simple that it only took 5 weeks to implement. The first draft describing the 6RD mechanism and freeze deployment was submitted to the IETF in February 2008. It was then published in January of 2010 as an informational RFC 5569. It was March 2010 that a working group approved that 6RD should become a standards track RFC. In August 2010, the standards track RFC 5969 was published. And finally, in the US, Comcast made 6RD software for home gateway devices available via open source for free, so the implementations took off from there. So the 6RD specification modifies functions of 6-to-4 to replace the standard 6-to-4 prefix of 2002/16 by an IPv6 prefix that belongs to the ISP assigned address space, so you no longer have that limitation of a 2002 prefix. Also, the 6-to-4 anycast address that was used for the 6-to-4 relay routers that connect to the IPv6 global internet is replaced by another anycast address chosen by the ISP. And that's one of the main things of 6RD is everything is under the control of a single ISP, and it's not relying on BGP updates and other messages to find IPv6 relays, as was the case with 6-to-4. The ISP then operates one of several 6RD gateways, which are essentially just upgraded 6-to-4 routers, at its border between its IPv4 infrastructure and the IPv6 internet. So it would require that the ISP itself have a native connection to the IPv6 internet. CPEs would support IP version 6 on their customer side and support 6RD upgraded from 6 to 4 functionality on their provider side. So the actual encapsulation of IP version 4 and IP version 6 is going to happen by the customer CPE. So before 6RD, so on the upper left you had your typical IP version 4 customer premise or CPE and CPE router, and then your ISP IP version 4 network, which in general your customer side would have a private IP version 4 address, and then on the ISP side of the CPE router you would have been defined an IP version 4 public address, and your CPE router would use NAT. And then you would have a carrier router connection to the IP version 4 internet. So this is the way that things have operated for years. After 6RD, the CPE router is actually upgraded through software to be a 6RD router and can encapsulate IP version 6 packets from the CPE in IP version 4 over an IP version 4 tunnel to a provider carrier grade 6RD gateway, which itself would have a native connection to the IPv6 internet. IP version 4 native packets would still traverse through the carrier router that connected the ISP's IP version 4 network to the IP version 4 internet. But now, from the customer CPE, we have IPv6 connectivity to the IPv6 internet. .6RD components and addressing, so you have an ISP IPv6 client, CPE router, the ISP infrastructure over which an IPv6 and IPv4 tunnel can be created, a 6RD gateway, an IPv6 internet, and the IPv6 internet client. So the link on the customer side is actually an IPv6 link, so the customer's client can actually be a native IPv6 client. Across the service provider's infrastructure, the CPE router will create an IPv6 over IPv4 tunnel. There's an IPv4 anycast address that's ISP assigned that the CPE routers knows would be the 6RD tunnel gateway. The ISP's IPv6 clients can use the IPv6 prefix of the ISP, and then the 6RD gateway can just announce a different subnet for each client. The IPv4 address of the CPE router is assigned as the IPv4 address of the customer site, and of course it will become the 6RD tunnel endpoint. So notice how the ISP IPv6 client creates a 6RD address using the ISP's IPv6 prefix as well as the IP version 4 address of the ISP side of the CPE router, followed by the ISP client's interface ID. Then the CPE router can make a simple decision. Does it use an IPv4 route to the 6RD gateway, which is the case when the ISP's IPv6 client wants to communicate with an IPv6 internet client, or if it's just another client within the ISP's routing domain, it can use a tunnel to another 6RD CPE. So when comparing 6RD to 6 to 4, with 6 to 4, connectivity to the IPv6 internet is best effort. There is no guarantee that there will be working routes toward the 6 to 4 relay. A 6 to 4 host is not guaranteed to be reachable by all native IPv6 hosts. An operator of a 6 to 4 relay has no control over which hosts use it. Operators also have little incentive to maintain a good quality of service as the traffic grows. However, with 6RD, each ISP uses one of its own IPv6 prefixes instead of the special 2002::/16 prefix standardized for 6 to 4. Therefore, a provider is guaranteed that its 6RD hosts will be reachable from all native IPv6 addresses, and there is no relay server to be used outside of its own control. Therefore, it also keeps full responsibility for the quality of service experienced by its own customers. 6RD also reduces the scope for traffic anonymization attacks such as those possible with 6 to 4. Well, as we switch gears and talk about some more transition mechanisms, let's talk for a moment about traditional network address translation, or NAT. Most of us are familiar with private IPv4 NAT to public IPv4. That's also referred to as NAT 44. With it, the service provider infrastructure uses public IP and the CPE only performs a NAT. More recently, we've used private IPv4 NAT at the CPE to private IPv4 translation on the service provider's backbone. Finally, somewhere at the edge of the service provider, translate that to a public IPv4 address. So there you have two actual NATs going on, private to public, or NAT 444. So the service provider infrastructure also uses a private IP, but as a public-facing interface. That enables a larger scale of using public IP addresses with more private clients behind it. However, at the service provider edge, it does require a large-scale NAT solution, or LSN, architecture, since the provider has to NAT to, not just the CPE or home modem. Of course, there can be scaling issues with that. So another technique could be private IPv4 NAT to private/public IPv6 to an IPv4 public address, or NAT 464. However, that would require the CPE modem to translate from IPv4 to IPv6. And as we'll talk later on in this topic, translation is not always that easy. It also would still require a large-scale NAT to also translate from IPv6 to IPv4 at the service provider's edge. So NAT 464 is not considered a very good solution. So what would be the best solution? And this is what we're going to talk about on the next few slides. There's another technique referred to as DS-Lite, where the CPE only has to tunnel IPv4 and IPv6 towards the provider, so the CPE doesn't even have to perform NAT. So similar to what we talked about with 6RD and 6-4, but in this case we're talking about the CPE being IPv4 and the service provider's backbone being IPv6. So now the large-scale NAT only has to perform NAT 44, so just one conversion of NAT. Of course, it would be a tunnel endpoint too, but as we've described, for instance with 6RD, that's just a simple software upgrade. So DS-Lite is defined by a draft DS-Lite broadband deployments following IPv4 exhaustion. It allows IPv4 CPE hosts to reach an IPv4 NAT at the service provider's edge over an IPv6 tunnel between the CPE modem and an ISP router. It is a better way to share IPv4 addresses among customers. Public IPv4 addresses on the internet side of the service provider's edge, not in the service provider's network. It combines two well-known technologies, IP, IPv4 and IPv6 tunnels in this example, and network address translation. It also enables both continued support for IPv4 services and incentives for the deployment of IPv6, because if the service provider's backbone is already upgraded to IPv6, it's a real good incentive for customer CPEs to do the same. So this is the DS-Lite architecture and the terms before and after. Sort of a funny way to refer to it, because before is on the home link side, so before we actually do any translations, and after is at the edge of the service provider's network, or after we've done the translations that we have described. So the before device is referred to as the basic bridging and broadband element, which is essentially the customer's CPE. And if you remember, as I described a moment ago, the customer's CPE is not required to do any translation, rather just tunnel the IPv6 packets in an IPv6 tunnel. The after gets its name from the address family translator router element. The after, as I described earlier, is a large-scale NAT or LSN. Anytime you have to do NATing at the edge of a service provider's network where it connects to either an IPv4 or an IPv6, you can expect there's going to be a lot of connections going through it, hence the term large scale. So I'm going to cover three scenarios for DS-Lite. The first one being existing IPv4 customer. So in this case, the customer, as you can see at the bottom of the screen here, has a private IPv4 address of 10.1.1.1, and its CPE is going to just encapsulate the packet over the service provider's IPv6 infrastructure, but not have to worry about doing any NAT. The NATing is actually going to occur when it gets to the edge of the service provider's network, the LSN, which has a mapping between the inside IPv6 plus IPv4 source address for the tunnel and then an outside public IPv4 address. So it's a simple way to provide connectivity to existing CPEs that are using private IP addresses across the IPv6 network of the service provider and then translate it back to a public IPv4 address for connecting to the IPv4 internet. Scenario number 2. So since the service provider's network is already IPv6, then a customer can add a home gateway that supports both its IPv4 and IPv6 protocols. And so IPv6 native traffic, a client at the customer side can just be configured with an IPv6 address, and then IPv6 packets can be routed through the IPv6 network of the service provider to the IPv6 internet. Whereas IPv4 traffic from the customer would have to be encapsulated and translated as I described in scenario 1. For scenario 3, it is possible for a customer to be dual stacked to run both IPv6 and IPv4 traffic and directly connect to the ISP without even using a CPE modem. So scenario 3 would combine both scenarios 1 and 2, 1 for the IPv4 traffic and 2 for the IPv6 traffic, but provide the customer a native link into the ISP without even having to go through a CPE modem. So now that we've described some of the most common tunneling mechanisms used today, 6-to-4 to tunnel IPv6 packets across the IPv4 internet, and 6RD to tunnel IPv4 packets across a service provider's IPv4 network. Also DS-Lite to tunnel IPv4 packets across the service provider's IPv6 internet. There are some other tunneling mechanisms out there for more specific types of stuff. So to start with, there's Teredo, which is a tunneling protocol designed to grant IPv6 connectivity to nodes which are located behind IPv6 unaware NAT devices. So it provides a way of encapsulating IPv6 packets within IPv4 UDP datagrams that can be routed through NAT devices and on the IPv4 internet. The Teredo protocol performs several functions. It diagnoses UDP over IP to determine the kind of NAT present. It assigns a globally routable unique IPv6 address to each host using it. It encapsulates IPv6 packets inside UDP IPv4 datagrams for transmission over an IPv4 network, which includes NAT traverso. And it routes traffic between Teredo hosts and native non-Teredo IPv6 hosts. There's also the generic packet tunneling in IPv6, which describes mechanisms by which a packet of a different protocol is encapsulated and carried as a payload within an IPv6 packet. The IPv6 tunnel broker is described in RFC 3053. Tunnel brokers can be seen as virtual IPv6 ISPs providing IPv6 connectivity to users already connected to the IPv4 internet. So for instance, you using your ISP's connection at home, you can find a public tunnel broker available such as GoGo6 to provide you that connectivity. Just Google GoGo6. Some service providers have implemented their own to provide IPv6 connectivity to their customers over their existing IPv4 backbones. One thing about tunnel brokers is the implementations require special application software to be installed on your client. RFC 2529, also known as IPv6 multicast tunneling, has long been deprecated. There's also a variety of translators out there. The idea of translators are to actually rewrite the IP and possibly application layers. So instead of tunneling, they take an original IPv4 packet and translate it to an IPv6 packet and vice versa. There have been a variety of different types of translators written, whether they have to work at just the network layer including the transport layer, and also if they need to include rewriting the application layers as well. So a network layer translator called Stateless IP ICMP Translation Algorithm, or SIT, was described in RFC 2765. SIT actually replaces packet headers IPv4 with IPv6 and vice versa. It also translates ICMP messages and fragments IPv4 messages to fit the IPv6 MTU when necessary. Another network layer translator is NAT-PT, but there's a major issue with NAT-PT because it breaks DNSSEC and therefore has major security issues. Therefore, the replacement for NAT-PT is now called NAT64 and offers a translation between IPv6 and IPv4 in much the same way as NAT-PT. NAT64 is combined with DNS64 to create the complete translation package to allow IPv6 clients to access IPv4 servers. Another network layer translator, Bump in the Stack, is described in RFC 2767 and is where the translator resides on the host and allows IPv4 applications to run on IPv6 hosts. Transport Relay Translator, or TRT, described in RFC 3142, is a TCP/UDP relay translator and translates both the IP and TCP layers from IPv6 to IPv4 and vice versa. As far as application level translators are concerned, Bump in the API is described in RFC 3338 and allows dual-stacked IPv6 hosts to use IPv6 applications. It has the same goal as Bump in the Stack, but translation is between IPv4 and IPv6 APIs, or application layer interfaces, and so therefore no header translation is required. Application layer gateways are necessary when the application layer contains an IP address, such as the case with SIP and FTP. So application layer gateways have long been used in firewalls and some NATs even for just IPv4. Thank you for taking the time for viewing this topic of the Demystifying IPv6 course on IPv4 IPv6 transition part 2.